Okay, so Math 2400, Lecture 7, Random Variables 4. In fact, we're still in Discrete random variables. And we discuss binomial, probability distribution. Binomial is the basic for so many things. In fact, that is the discrete version of normal distribution. So it's important to understand this carefully. So, what is the problem? The problem is we perform an experiment and it has two outcomes, success S and failure F. And we do it n times. The goal is to find the following probability of X successes in n trials. And this X is in this situation, X is just an integer, right? Integer ranging from 0 to n, right? 0 success means you fail all the time. And n successes means you had n successes, right? So what is an experiment? Most experiments that we perform are like that. Well, the simplest one is like tossing a coin, for example, or it's either heads or tails. So that's like if you say head is success and tail is failure, then it's success or failure. Okay, so let's analyze this carefully. So experiment, let's call it experiment. No, let's experiment. Experiment 1, experiment 2, experiment, let's write the last one, experiment. Okay, so I put the question mark here because I don't know how many such experiments exist. Okay, so, well, experiment 1 can be like this. So I have n, can be like success, failure, success, failure, maybe the last one, whatever that is. And the second one like this, it might be this, it might be this. And so on. Okay, so each experiment gives me, and I'm assuming that these are different. Okay, so if I perform and I get this, and I get it again, this configuration, then I just write one of them. So this, I should have said configuration 1. So configuration 1, configuration 2, and configuration, who knows how many. So configuration means this can happen many times, the same configuration. So I might have, if I'm like doing it 5 times, 1, 2, 3, 4, 5, then this is the configuration, right? So it might happen many times, but this is one configuration. And when I say what's the probability of this happening, I'm doing it one time, right? I'm doing it one time and I'm asking this question. What is the probability of this configuration happening in some experiment? So maybe I should erase this and stick with the configuration, because the experiment might say, okay, well, you can do that a million times. Okay, let's look at one configuration. So let's look at one configuration. Say this first one, no difference. So let's take one of them, like the top one. So S, S, F, S, F, then the last one is like before. So what is this? I am saying, what is the probability of this happening? So what is the probability of this thing? Okay, what is the probability of this configuration, say on top, happening? Okay, this is well, these experiments are independent of each other, right? When you toss a coin, boom, first time, second time, third time, fourth time, and so on. Each time is independent from the previous one and the next one. So each one of these is an independent event. This event is independent from the rest event. So this event of getting an S in this position, that's what I'm talking about. Getting an S in position 1 is independent from getting S or F in position 2 and so on. And this is what? This is like P of S and S and F and F in the end, right? So it is P of this event happening, S in first position, this event happening, this event happening, this event happening. It's and, right? And. And these are independent events. So what was the formula, or what was the procedure of finding a probability of independent events when you have and between them? This and this and this. Remember that I guess we call it multiplication rule or product rule or whatever we call it. So this is in fact the probability of the first one happening, then the second one happening, and so on. So it's the product of these probabilities happening. I mean, the product of these probabilities. So it is P of S, until the last one, P of F. So because these are independent events, each one of them is independent from the other one, and because it is and, it is this happening, and this happening, and this happening, and we have a rule for that, the multiplication rule or product rule, whatever, and that is, it says that the probability of this happening, this whole event happening, is the probability of the first one times the second one times the third one, and so on. So, probability of one of these configurations, which I took just the first one, happening is this. So it is some probability of S times probability of S and so on. So now we have to look at this and say, okay, how many S's do I have here? How many S's do I have here? So what was the problem? The problem was having X successes in N trials. So I have X S's here, or X PS's here, and N minus X PFs. So this thing, well, let me write it here. I have PS, and the last one was my PF. That is that thing over there. And here I have X PS's and N minus X PFs. Okay? So let's let P of S be simply small p, then P of F, failure, is the complement of that, so that is 1 minus P, right? Okay? 1 minus P. So this configuration, the probability of this configuration happening is this. So that will be, I have X P's, P to power X, and I have N minus X, 1 minus P's. Okay? So the probability of this happening is this. How about this one? That's the same thing. I have x p's here and n minus x f's. Blah, 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 until the last one, right? So the probability of each configuration, is simply p to power x times 1 minus p to power n minus x. Okay. Now, let me erase this because I'm going to discuss those. So, this was like going this way, like row-wise. So I just look at it row-wise, and I realized that each row as a configuration has the same probability as the other row. So they all have the same probability. Now let's look at them this way. So we have configuration 1, configuration 2, configuration blah blah up to configuration question mark. And these are mutually exclusive. What does it mean? It means either this happens, or this, or this, or this, right? That's or. There's or between them. So if you toss the coin 5 times, something happens. One of them happens. But can the other one also happen at the same time? No. One of them happens. So I should find the probability of this. So I should find the probability of configuration 1 or configuration 2 or configuration question mark. And they are or. And they are mutually exclusive, right? Not just or, they are mutually exclusive. Either this happens or this or this or this, right? So one of them happens. And remember, when we had mutually exclusive, then this is simply adding them. So this is probability of configuration 1 plus probability of configuration 2 up to probability of configuration question mark. So how many such probabilities do I have? Question mark. Okay, so each one of them has this probability, so this is in fact that question mark, whatever that is, times px 1 minus p to power n minus x. So this is in fact, comes down to this, comes down to finding this question mark, right? So I have to find this question mark, which means how many different configurations do I have? So let's see what this question mark is. The question mark is this. The question mark is counting, right? I should count number of such configurations. What is each one of them? Each one of them is like distributing x s's in n positions. X s's in n positions. What is that? That is n choose x, n choose x. Do I have a order or it's unordered? It's unordered. There is no order here. It just those s's can be anywhere, right? There is no order. So this is n choose x without order. Okay, so what is that? That's simply c n x, or as we wrote it in this binomial form, nx. Right? So this probability is in fact probability of conv 1 or conv 2 or what's the last one? Conv And oh no, that is the, yeah, that's it. So is in fact nx p to power x 1 minus p to power n minus x. Okay? So, that's it. That is the probability that I was looking for, probability of x successes in n trials. So let me erase everything and write it down. So let x be the random variable, which is x successes. No, number of, sorry, what x? Number of successes in n trials. N trials, then p of x being small x is nx p to power x 1 minus p to power n minus x. Now, this is in fact when x is an integer between 0 and n. Otherwise it is 0. 0 otherwise. Okay. So it's not just that interesting formula, it is also otherwise. Okay. Now, one thing is, why is this 1? Why? X starting at 0 going to n of nx p to power x 1 minus p n minus x. Why is this 1? Remember that distribution should add up to 1. I mean the PMF should add up to 1. In fact, that is what we call, I guess the book calls that PX or FX, the PMF. So remember the PMF should add up to 1 over the x's, over the points it chooses, I mean x takes, over the image of x. Say this is the image of x, goes from 0 to 9. And why is it 1? Look at this, where have you seen this thing? This is like binomial distribution, right? So this is binomial distribution, and let me write binomial distribution here. Remember, recall if I had x plus, let's write a plus b, so doesn't confuse me, but x. So if I have a plus b to power n, remember that was, what was that, like r from 0 to n, and r, a to power r, times b to power n minus r, right? Times b to power n minus r. Let's compare. This is like a to power x, and this is like b to power n minus x. Compare with that. So this is in fact what? This is in fact this as a, this one as b to power n. So that is 1 to power n, which is 1. Okay? So in fact that adds up to 1. Okay, so what else should we really find? There are two other things. Remember, for any distribution, we have to find two things: the expected value or mean, and variance, which also gives me standard deviation. So I have to find those two for this distribution. Let's go to the definition of these two and try to find it. So expected value, so what was E of x? Remember, that was sigma x from 0 to n x times fx, right? So it is sigma x from 0 to n x times n x p to the power x 1 minus p to the power n minus x. Well, there are different ways to find this, but there's an easy way to do it. But that easy method needs some more knowledge of random variables. But let me, it's good to start early on something. So let's look at each one of those configurations. So remember the configurations, one of those configurations, configuration say J, whatever. So each one of these trials, say each one of them is a Bernoulli process. Is the Bernoulli process, right? What was Bernoulli process? You do an experiment one time, and it has two outcomes, two possible outcomes, success or failure, and the probability of success is P, failure 1 minus P. So each one of them is a Bernoulli process, and all of them are the same. All of them are the same. So it's like this one, if I call it x1, x2, xn, each xi is a Bernoulli process. Each one of them is a Bernoulli process, right? So what do I have here? And what is x in fact? X was what? X was number of successes. Okay. X is number of successes. What is xi? Xi takes 0 for failure and 1 for success, right? So xi has two values, 0 or 1. It takes two values, 0 or 1. 0 for failure and 1 for success. So if I add them, then I will get x. Right? X is number of successes. Each success, xi takes 1 for success. So if this is success, blah, 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 something, then number of successes, in fact, is the value that each one of them takes. Right? So if I have like 5 successes, 5 of them is 1. The rest are 0. So you might say, what are you talking about? You're adding random variables? Yes, I'm adding random variables. That goes into more than one random variable. So considering more than one random variable, multivariate or something. And in fact, what we will be discussing at some point is multivariate. You can't ignore. You cannot just say no, just stick with one, because statistics, you would see that it relies on this. I mean, it's all that. You're doing some experiment a million times, or you have a data, say, the chart which has like 10 million rows. So you are dealing with that. But anyway, we can say that the binomial is in fact the sum of some Bernoulli, say, processes. In the sense of binomial with n triads and x successes, if you call that, that is in fact the sum of some Bernoulli processes. So binomial process is the sum of Bernoulli processes. Some special Bernoulli processes. Yeah, okay. Now, why is it good? It's good to find that, right? So, if instead I write it as x2 up to xn, this is x, and if I use that fact that e acts like a linear function, so it just distributes over addition, this will be e of x1 plus e of x2, e of xn, and each one of them, remember the expected value of Bernoulli was p plus p, that is n p. So without doing anything else, which I guess I'm not sure what the textbook has done here, but just using some facts about expected values, I have come up with this. Okay. So, that is the expected value of binomial distribution. Now, what is its variance? Well, variance also is the same thing. But let's use that variance. Remember, variance of x was e of x squared minus ex squared. E of x squared is this sigma x squared instead of x. And x, p to the power x, 1 minus p to the power n minus x. And x goes from 0 to n, plus, minus ex is np, squared. Okay, so I have to find this sum. Again, there are ways to find this sum, but why not using properties of variance? And the fact that this x is a sum of some Bernoulli random variables. So instead of this, I can write it as variance of x1 plus x2 plus dot 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 and xn, and its xj is in fact Bernoulli p. What was variance? Variance, there was this rule for variance, remember? Variance of ax plus b was simply a squared variance of x, right? So b would go away. So this will be, if I extend that to more than one random variable, I will get it is in fact variance of, there's a 1 here. 1, 1, 1, 1, 1. So it is 1 squared. There's a 1 squared. Variance of x1 plus 1 squared. This is 1. Variance of x2 up to the last one. And then 1 comes from the fact that each one of them has a coefficient 1. If I have 2x1, I would get 2 squared. 10x1, 10 squared, right? So using that formula, that's what happens. Okay, so what do I need? I need variance of Bernoulli. Variance of Bernoulli P. Okay, so let me erase this and try to find variance of Bernoulli P. So I need the variance of y, say, when y is Bernoulli P. So what was the y? So probability of y 0 is 1 minus p. Remember, probability of y is 1 is p. So what was variance of y? Variance of y is expected value of x squared minus expected value of x squared. And sorry, y, this is y, not x. Y squared and y. Okay, so what is this? We found this thing, expected value of y is p. We found this one, so that's p. What is this one? So this by definition is what? Is x times y squared, so it is y squared f of y. So this is f of y. Okay, so this is not f of y, in fact that is f of y is this. Okay, so that's f of y. So what do I have? So y squared, the first one is 1 squared times p plus 0 squared times 1 minus p, and there is a p squared here. So that is in fact p minus p squared, and that is p times 1 minus p. Look at it, this is not negative, because p is between 0 and 1. P is probability, and probability is between 0 and 1. So, variance of y is in fact p times 1 minus p. So let's go back to what I had before. So variance of y, we found that it is p times 1 minus p. And now we had variance of x was variance of x1 plus xn, and that was n times variance of x. One of them, x1, say, because x1 and x, all of them are the same, so that is n p 1 minus p. So variance of the binomial is n p times 1 minus p. Okay. So what let's summarize this thing. So we found that f of x, the PMF is in fact n x p x 1 minus p n minus x. And I guess the book uses some notation for this, doesn't it? Bxnp. Oh yeah, so it says Bxnp. Bx. The book uses this, Bxnp. Okay. So x is the number of successes, n is number of tries, and p is probability of one success. Now, on your calculator, you probably will find it as binomial x or n xp, something like that. I can't remember. This is when x is an integer, 0, 1, 2, up to n, and 0 otherwise. So when I find my calculator, I will tell you what it is. But you can check distributions. There is some place button which says DISTR distribution, something like that. And if you push that, you will see at least you can recognize this one. It might have binomial. I'm not sure if it has, but it does a binomial, normal, Poisson, and other things. So that's it. So that is the okay, and expected value on mu was simply NP, and the sigma squared, which was variance of x, is NP1 minus P. Okay, so that is, now let me give you an example. Well, examples are just simple, but let me give you an example and also discuss this thing a little more. So let's see. Let me erase this. So a problem can be something like this. So a fair coin means what? So fair coin means this. Means the probability of getting a head is 1/2 of 50.5. Okay, so fair coin or fair dice, for example, means that the probability of getting any number on the dice is 1/6. So fair coin means 1/2. So what is P here? If a fair coin means that means probability of success. This is heads, i.e. heads is P, and tail is also on the same. So success here means, let's say, that's our definition. It doesn't have to be heads. You say, no, I don't like heads, I like tails. So for me, that is success. Well, anyway, in this case, P is in fact 1/2. Okay. What is the expected number of heads? Well, if you didn't know any probability, or you haven't taken this course or any other course, what would you say? Just as if you would just ask a kid and say, what do you expect if you toss this 100 times? How many heads do you expect to get? Well, they say 100 times, that's 50, right? The expected number of heads is 50. Even without knowing any probability or just discussing these things or knowing the expected value of this x. So if x is number of heads, then P of, expected value of x. So expected value of x, so that's part A. Expected value of x is simply NP, which is 100 times 1/2, which is 50. So expected value of x, which is the expected number of heads, is in fact 50. That makes sense, right? So you expect 50 of them to come up heads. Now, what is the second one? What is the probability of getting 75 heads? That is binomial what? So part A, the solution, the answer to part A is 50, and the part B is that is B. Remember, that is B of what was that? 75. 75. What was that? NP or PN? What was first? NP. So 100 and 1/2. So that is in fact 175 times 1/2 to power 75, 1/2 to power 100 minus 75. So if I simplify that, that is 175 times, well, that is 25, so that's 100 to power 100. Well, you can guess that this shouldn't be a large number. 75 heads in 100, that's a lot. Then you should be very lucky to get 75 out of 100. So, and you can see that this is 0.5 to the power 100. Just do it on your calculator. Well, you have to do it to do them together. Otherwise, you will get 0 here. That's almost 0. But this is also a large number. So a large number times a small number, you will get something. I don't know, maybe when you get 0, it just tells you, oh, that's almost 0. It's not 0. It's not 0. It's close, maybe close to a very small number. So, as I said, I don't have my calculator here. So, let me just stop here. So, the binomial, which is the building blocks of, as we will see, other distributions like Poisson, for example, which is again another discrete distribution we will study in a few days, and then normal distribution, which comes in continuous random variables chapter of the book. Okay, so let me stop here and see you next time.